on one hand, we're serving operators with metro transport solutions, so real active or passive systems for metro distances, transporting all sort of data on the other end. And this is where we're here today, making fiber optic components, passive muxes, most of all, and all variants of those, and also optical engines, ROSAs and TOSAs, and the coupling module I mentioned today, being used on chip-on-board assemblies. Before we go into how we solve the challenges, let's look first back in history. So what are actually the challenges in optics and transceiver optics? So let's look back in history. So around 2010, the dominant form factor was the CFP with 100 gig, and also this variant of LR4 having multiple lambdas, so multiple colors, lasers inside, and four photodetectors. And that was a discrete assembly of multiplexes with fibers and connectors connecting to individual TOCAN-based lasers or photodetectors. And so rather bulky assembly of separate discrete components, and hence requiring a big form factor, the CFP, nicely addressing that, but not the whole industry was overly happy with a big size. And so there was this pressure to make it smaller, so the transceiver had to shrink. And it went around 2015. The QSFP was dominant, and enabling this was to put all these functions of muxing and demuxing photodetectors and that into so-called gold boxes. So integrating it, getting rid of the fibers in between, and having assemblies in hermetically sealed gold boxes, also of the price of a golden box, so to speak. So now, today, there's further integration. So the transceiver size itself is not the problem. It did not shrink anymore. However, as we get to higher speeds, the functionality inside has actually highly increased. So no longer 4 lanes. Now it's actually even up to 8 lanes inside. And there's this tremendous cost pressure. And that required to get rid of these gold boxes and do then also the much smaller in overall size assembly of these photodetectors and lasers directly on the PCB board of the transceiver, so chip-on-board technology. However, you still need to couple into the fiber and to multiplex. If we look a little bit further, so on the horizon and already starting co-packaged optics. So this is a picture from Inphi that is their design, and addressing this requirement with the higher data rates on the switches and routers, that you need to package the transceiver functionality co-packaged to the switch ASIC or near package and all these variants, as this tremendous data rates you cannot transport or not easily transport over the copper lines of your PCB board to the front plate, hence these co-packaged transceiver optics. But now these drive even more challenges. So now you don't have any longer 4 or 8 electrical lanes, which you need to translate into fibers. You get up to more than 1,000 lanes. So that would mean a huge fiber count. And you don't want to handle thousands of fiber on your board, so you can reduce the number of fibers by having multiplexes in that. You still need to couple. And with this approach, you're also now getting very sensitive to polarization. So it gets smaller. So the tolerances, because of these many lanes side by side, they get even more challenging. And as already mentioned, you have with the smaller distances, the channel spacing, so the spacing between photodetectors or lasers has to decrease. So that's driving the tolerances down. If we look on the challenges in a little bit more detail, so as an example, couple light out of the laser or back into the photodiode. As an example, we're looking here at photodiodes. So there are different diameters around a photodiode. So you can see 20 micron diameter, 2 versions, and a 16 micron PD, or even grating couplers. And then if you look at this active area of these photodiodes, so where they really are sensitive to the incoming beam, and the colors are indicating the different loss levels. So the dark blue would be 0 dB loss, whereas the dark red, you're already in the more than 3 dB loss, so not really acceptable. And so this shows you at 100 gig, in the old CFPs, they used typically lensed 20 micron photodiodes. So that gives you what we call a 45 micrometer plateau. So it's actually an effective area where you can successfully, with a low loss, couple into the photodiode of 45 microns. So it's huge. And there is also, well, of course, with the speed, the photodiode decreases. So, and with the QSFPs, we already see these photodiodes of 20 micron, still 100 gig application. And although it's 20 micron diameter, the really usable area is only 14. And if you go to higher speed photodiodes, 400 gig applications typically used is the 60 micron PD. So that only remains as an 8 micron plateau. And whereas with the grating couplers commonly used with silicon photonics, it goes down to 3 micron. And here it's also very important, the angle in which you're using to couple into that. So you see that the precision is increasing, the required precisions by magnitudes of order. And while the active area is important, or the precision to get a low insertion loss, what you want to receive, on the other hand, you do not want to have backscattering. So, and this means you want to drive up the return loss as high as possible. So if we look at, this is the example of a 16 micron PD. So if we look on this active area here now, then this would be the same here. And if you go into that PD on an angle of 0 degree, you'd have a lousy return loss. It's only 30, 35-ish dB, and that would not be acceptable. So you need to tilt the angle a little bit of the beam. That, of course, decreases your active area, but only slightly. So you have to find a compromise, but then at an angle of 11 degree, as you can see here, you bring it up, the return loss to around 50 dBs, and you can still have a very good insertion loss performance. So how do we address these challenges? What we have developed is what we call the WDM coupling module, so a multi-lambda wavelengths division multiplexer module to couple into photodetectors or out of lasers. And this is the principle. There are different variants around, actually, but showing here a 4-channel version. And you see it's ultra compact. It's about 3 by 5 millimeters and just around 1 millimeter height. And it features, of course, the input fiber. So that would be on a chip on board transceiver. That would be the part sticking out of the transceiver where you connect your patch cord. And then you have this fiber connecting to the module. And then we hand over the beams out of the fiber demultiplex to this PCB board, which is made by the transceiver maker, and that hosts the photodetectors or the lasers. So how does it look inside? Let's have a look through the PCB from the bottom. And so we look from the other end. So here you can see now, this is the input fiber. And we then have a beam bouncing multiplexer setup. So a cascade of thin film filters here. And the incoming light bounces between those filters, and the filters pass or transmit one lambda, for instance, so-called blue or the green, and reflect the others. And so therefore we sort out one by one channel after the other. And then this is focused on the photodetector, vice versa. This could be also a laser, then it's the other way around, and we couple into the fiber. So inside this optical part here, so here's where we do the beam shaping and the steering it or reflection. This is a parabolic reflective optics, which is typically done with a polymer injection molding process. So it's a polymer piece part, and the reflective areas are actually coated with gold to be reflective. And so here we have the filter cascade sitting on a glass block, and the backside is a mirror to work. And here you see the mounting on the PCB board. There is also an RFID chip included that hosts the specific data of that module. I'll come to that in a minute. And what we see as one of the biggest advantages is providing a great performance in terms of coupling and optics, but also a very important thing is the ease of assembly for our customers. So it's basically a very simple 3-step process. You grab that part by a vacuum gripper. We provide the gripper, the tool to align automatically to this coupling module. So you grab it, you place it over your PD lasers, and you find the middle position, and then you put it down, and there's no height alignment necessary. There's an automatic stop by the coupling module itself, and you just glue it to your PCB board. So it's a very simple, straightforward process, which is easy to automate. And here we see how an automated assembly can look like. So here you see the spots of the coupling module of the light on the photodetectors, and we have alignment markers which you can see in your alignment process, in an automated alignment process with a visual tool cameras looking onto that, and you can then auto align. The specific beam position data of each module is stored in this RFID chip. You can load it into your assembly machines and then facilitate the process. Let's have a look on the performance. So this is a little bit showing the precision. So it's the beam positions of each of the 4 beams, the X direction, the Y direction. So here in the X, we're better than 2 micron precision. The Y is even below 1 micron. And more interesting, so the beam characteristics. So we have an extremely flat top bandpass filter. So that is intrinsically coming out of the thin film filters compared to AWGs, so which are rather Gaussian shaped. So we have a real almost rectangular flat top. And typically the insertion loss is much better than 0.5 dB. And it's also very low PDL, around 0.1. And as a summary, this is the whole universe, so to speak, of these different coupling modules. So of course, we're having different photodiodes, as mentioned. So we adapt to the specific photodiodes or to the lasers, and different applications require different amount of channels. So there are different versions around not necessarily 1 channel, but 2 to 8 channels. We do TX and RX, as mentioned, as separate or combined. There are also BiDi versions, just 1 fiber sending and receiving within 1 coupling module. We adapt to the different pitches. So the photodiodes and lasers, they're not only coming in different diameters, but also in different pitch sizes. Very common are 250 micron to 750 micron pitches. Obviously, then the width of the coupling module changes with the width of your PD array. As mentioned before, we have to adapt the beam, or we adapt the beam angle to the specifics requirements, and it's polarization maintaining, which is a key factor for chip on board designs. And of course, all the different WM grids are supported by the thin film filters, even SWM, and also just parallel optics. So there's a slightly different version for parallel non-filtered setups. So as last, I'd like to make a small comparison between the 2 technologies that we see around for chip on board. So one is AWG, so array waveguides in glass chips and glass substrates typically, and versus ours. So let's start with the pricing. It's always the most important question. It's a similar cost structure. There is not really a difference. The usability. So on AWGs, this chip, you always need to a line in a rather complex assembly process, again with filters with lenses to the fibers, and it can get very critical for small detectors. What we've seen, we have a very simple, depending on the design, you can do a full passive assembly process with these markers. The beam is probably the biggest difference. So we have a real single mode beam characteristic, no Gaussian beam shape, which is slightly multimode. Even in single mode applications or especially in single mode applications, that can be a big disadvantage, and very high loss on the AWG side compared to a very low loss on our end and the flat top filter. Okay, I would be happy to answer any questions after our talk, or you can just write me and contact me later via Hugo and Sune.